Hello, ladies and gentlemen. Okay, this is Unit 6, Day 3, and we're talking about solving equations with logarithms, okay? And so in this particular lesson, there are going to be 3 types of logarithmic equations, okay? The third one being the easiest, all right? Third one involves just as long as both sides, as long as on both sides of the equal sign, the bases are the same, condense each side to a single log expression, then drop the logs and solve, okay? So this one's the easiest in the sense that just like when we had with, let me write it out here. Whoops. Okay, if you go back to our exponents unit, and we had something like this, right? And I said, okay, once we have the same base, what do? We drop the base, and then we solve for x, okay? Same sort of thing applies here. When you encounter something like this, which we will see later in the chapter here, right, we have log on both sides. Both have the same base of b. You would drop the logs, and then you would just set these equal to each other and then solve. Okay? So, 3 is the easiest one of them all, in the sense that all you're looking for is whether or not you got log on both sides, same base, drop the log. Okay? The other 2 involve a little more work. Okay? So the first one involves what says if there's no logs on either side of the equal sign and the variable is an exponent, okay, like you see in case 1, all right, you're going to isolate the expression with the exponent variable, take log of both sides. Okay, so let's go ahead and just do that. All right, before I start talking any more about the other ones, okay, let's just go ahead and demonstrate that first case. All right, also, you can never take the logarithm of a negative number. And then also the log of 0 is undefined. Okay, remember the graph of this guy, okay, from that first chapter, okay, when we had you graph the exponential equation 2x, okay, remember the inverse of that looked something like this. And this was the log 2 of x. Okay? And so, if you look here, we're getting an asymptote for this guy right here at x is equal to 0. Right? So it makes sense that we can never take the log of a negative number because technically, right, in dealing with logs, there is no negative number. And of course, it never reaches 0, so we can never have an x value of 0 when solving for logs. So you can never take the log of a negative number, or can't never take the log of 0 because, well, neither one of them exists. Okay, so not all answers necessarily work. Check them. You need to make sure that the answer will not cause a negative or a 0 to be next to the log. Okay, and so that's what we're looking for. All right, so don't know if there's too many extraneous cases in this one. I cannot remember. I don't think there is, but it's just something to look for in the future. Okay? And so anyway, this is case 1, right? And what does case 1 say? No logs on either side. The variable is an exponent. Look in number 1 number 2. No logs on either side. Our variable is an exponent. And it says isolate the expression with the exponent variable, which means get this piece by itself, which as you can see, we got that in both cases. And then our last piece, it says take log of both sides. So we come down here, we're going to say the log of 2 to the x is equal to the log of 7. Okay? And then using our power property, I'm going to take that x and I'm going to move it to the front of the log. Now why did I do that? Well, our x is no longer located as an exponent. It's now kind of on the same level as our log of 2 and log of 7. So and basically it's just x times log of 2 is equal to the log of 7. So what we have to do to solve for x, divide both sides by the log of 2. And so x is equal to the log of 2, or 7 divided by the log of 2. So let me get my calculator. Okay, so the log of 7 divided by the log of 2 gives me 2.8074. Okay? Now, does this make sense, right? So we know that 2 to the third is equal to 8. And we know that 2 to the second is equal to 4. Okay? So being that our answer is equal to 7, we knew that this x value, right, had to be somewhere between 2 and 3. Okay? More closer to the 3 range, right? Because it's closer. 7 is closer to 8 than it is to 4. Okay? So this makes sense. And if you're ever unsure, just check it out. So 2 raised to the 2.8074. Give it about 4 spaces behind it. Give you a more accurate answer. And you get 7.000218. So close enough. Okay? We'll just say, we'll put it in there, just 7.0002. All right, so close enough. Okay. Now, the next one, same thing. Take the log of both sides. Bring that x to the front using our power property. And then to get x by itself, I'm going to take the log of 15 divided by the log of 4. And the log of 15 divided by the log of 4 equals 1.9534. Okay, which makes sense because, again, 4 to the second power is 16, and so 4 to some power is equal to 15. We knew it's not going to be quite 2, but it's going to be pretty close. So 1.9534 sounds about right to me. Okay, go down to number 3. All right, and number 3, the difference between number 3 and what we have in 2 and 1 is that we don't have our variable isolated here, okay, with the exponent. Okay, so we have to isolate the expression with the exponent variable. So as you can see in number 3 here, all right, we got 3 variables here, right? We got this guy here, and this guy here. So all we have to do is take that 4 over to the other side. So we get 10 to x minus 3 is equal to 17. And then we do the same thing as we were doing above. Log of 10 to the 2x minus 3 is equal to the log of 17. Then I take that exponent and I bring it in front of my log. Okay? And then do the same process as we did over on the other. Okay, I'm going to divide by the log of 10, divide by the log of 10, which actually the log of 10 is just 1. Okay, so we get 2x minus 3 is equal to the log of 17. Okay, so we're going to get the log of 17 divided by the log of 10, which is just 1. And then, to get x by itself, I'm going to add 3. So just so I don't have a big long number there, I'm going to kind of keep those together. So x is equal to the log of 17 plus 3, and then all of that divided by 2. So the log of 17 plus 3, all that divided by 2. X is equal to 2.1152. Okay? And if you put that in there, we definitely would not get an extraneous root, right? So we're good to go there. All right, because 2 times 2.1152 will give us 4 something, minus 3, we're okay. All right, next one. Okay, case 2. What does case 2 state? So case 2 states that there's a log on one side but not on the other. So write as a single log expression first and then put into exponential form. Okay, so this is kind of what we were practicing on day 1. We were going from logs to exponential functions. Okay, so we're going to have to do the same thing here. So the first thing we want to do, though, is we want to get it so that we just have one log expression. Okay, so that's what they're looking for right here. Log with a base to something. So log 3 of 2 of x is equal to negative 5. That's what you're looking for. Okay, so once we have that, then we can just convert it to exponential form. So 3 to the negative 5 is equal to 2x. And then we're going to divide both sides by 2. So x is equal to 3 to the negative 5 divided by 2. And so whatever that is equal to, this gives us 0.00206. Okay, and there's our answer. Let's go down to the next one. Okay, again, we have to get it so it looks something like we do up above here. So I'm going to add 5. So I get 2 log of x is equal to 10. And then I could essentially move that 2 back here, but that won't do us any good here. All right? Instead of moving it and putting it back inside the log, I'm just going to divide by 2, just to get rid of that. And so all of a sudden we're going to be left with log of x is equal to 5. Okay? Remember, our base down here is 10. So it's saying 10 to the 5th power is equal to what? X is equal to 10 to the 5th power, or 100,000. Okay? And the last piece, again, we're going to have to utilize our properties to sort of put these guys together. So I noticed that we're subtracting here, and we got the same base, so that's good. So I can put these together using my quotient property. And then I'll say 2 to the 3rd power is equal to x plus 1 over x. 2 to the 3rd power is equal to 8, so 8 is equal to x plus 1 over x multiplied by x. So we get 8x is equal to x plus 1. Subtract x, 7x is equal to 1. Divide by 7. X is equal to 1/7. Okay. And the last part is the easiest one, right? So all we're looking for is, do we have logs on both sides? Do they have the same base? If they do, we drop the logs, and then we just solve. X is equal to 2. Okay? So nothing too crazy there, right? So again, same base, log on either side. 2x minus 1 is equal to x plus 5. Subtract x, x minus 1 is equal to 5, plus 1, x is equal to 6. And then lastly, we just have to combine these two guys. So first thing I'm going to do is I am going to use that power property. I'm going to put that 2 back. So we're going to have log 3 of 9 squared plus log 3 of x is equal to log 327. Okay, and then combine these again, so log 3 of 81x is equal to the log 3 of 27. Drop the logs, and so 81x is equal to 27 divided by 81. X is equal to a 1/3. Okay? All right. And then that's pretty much it. All right, so just have to make sure that we're not getting a 0 in any of those, which we're not. So we're good to go. No extraneous roots. And so we're okay. And basically what they're looking for is extraneous roots. They're looking for something like this. So if we came up with either this came to a 0, or if we plug that 2 in and we get, a -5 here, we cannot take those logs. Okay? So anyway, hopefully this was helpful. And